Hello, this is Tim Malloy with video 2-1 on energy, not 1-2. Oops. So I'm going to be doing number 18 off 4A. Let's get into it. An inclined plane of theta equals 20 degrees has a spring force constant, K, equals 495 Newton meters, or newtons divided by meters, fastened securely at the bottom so that the spring is parallel to the surface as shown in the figure below. A block of mass m equals 2.53 kilograms is placed on the plane at a distance d equals dot or 0.315 meters from the spring. From the position, the block is projected downward toward the spring with speed 0.75 meters per second. By what distance is the spring compressed when the block momentarily comes to rest? So if I draw in, this is our, I'll go back to one. This is the distance that the block covers without touching the spring. And now we have to find the distance that the spring compresses. Let's write down our givens first. Spring constant, K equals 495 newtons divided by meters. Distance between the block and the spring. Mass of the block. Initial velocity of the block. That should be an O, not an I. And then the what would you call this? The angle of elevation with respect to the horizontal. No mention of friction is made, so let's just not worry about that. I believe you should always start these problems off with an LOL diagram. So I'm thinking two positions. We have the start, which is the part depicted in the picture, the position depicted in the picture, and then the spring is at equilibrium. So we have some kinetic energy from the block's movement, and then we have some gravitational energy because as this block travels down, it is going to be accelerating due to gravity. I'll go back in more detail with that in a minute. And then at equilibrium, we have all of our energy transferred into elastic energy. So I suppose that this should be much greater, like that, to show that all the kinetic and all the gravitational energy goes into this elastic energy. So again, we have this acceleration due to gravity, which is kind of why the block is accelerating, because we have some gravitational energy, and the gravitational energy accounts for the acceleration that our block will experience. Very important, sets this problem apart from a 1D motion problem. You know, a regular 1D motion problem, usually just constant velocity, might be some friction, just smashes into the spring, see how far distance it travels. But in this type of equation, there is no change in velocity. However, we will have a change in the block's velocity due to the acceleration. I think that is the main takeaway from this problem, is that you have to learn how to be able to do these kind of spring problems with acceleration. And since we have gravity accelerating the block, that makes it a bit simpler. Again, acceleration becomes from angle and gravity. Just have a free body force diagram. Not a whole lot to understand here. Just, again, horizontal acceleration if we rotate the system. Okay, now that that tangent is done, I think that we've really understood the problem, that it's going to be a whole lot simpler from here. So back to the LOL. Let's set up an energy conservation equation. Kinetic plus gravitational equals elastic, and then I have their respective equations right here. K equals 1/2 mv squared. Gravitational, or U, equals mgh, and then elastic energy equals 1/2 K spring constant, or x squared. And then we plug that into the energy equation. We know from the problem that we have mass. We know that we have velocity. We have g, gravitational on Earth, 9.8 meters per second. Spring constant. We do not have x. We are solving for x. And we also do not have the h. So how far up is the block? Let's try to find this value and head back to the picture. So if we call our the part where the position where the block is no longer moving is at equilibrium, if we call that the point of reference, then we can understand that From the top of from where the block starts to where the block ends is the height. We set up this triangle, which includes the distance between the block and the spring, as well as what would you call this? The distance that the spring is pushed back. We make a triangle out of that. Sine of 20 equals h over 0.35 m plus x, and then we just multiply, and then we've successfully put h as a function of x, which is really going to help us out. Now we can go ahead and plug that. We can go ahead and plug in our values. You can see I plugged in what we solved for h, and then did some simplifying, more simplifying, quadratic formula, and then subtracting gives us a positive answer. So we can't use the negative on that. Just use the, or if we can't use the positive on that, I apologize. So we have to use the negative. Subtracting is a positive answer. So x equals 0.135 meters. Put that in the WebAssign. Everything's all good. So here are some takeaways. You really have to nail down the acceleration and the gravitational energy. I think I definitely did talk a whole lot about that, so there should be a little confusion. And again, when you understand how it's different from these simpler problems, then I think it makes it a lot easier to understand. And then the energy equations make this much easier versus using the kinematics. I first tried using the kinematics. You can see some leftover work down here. I was trying to find out what our velocity would be at this point right before contact is made. I have confidence I could have solved it that way, but it would not have been pretty, and I don't think it would have been in the spirit of this problem, which is to work with strictly the energy equations. Or at least I think if we work strictly with the energy equations, it makes the problem easier, gives us a better understanding of energy. So I think that's it for this problem. Thank you.